Welcome. In the last lecture, we have studied external direct product of groups. In this lecture, we'll study another type of direct product that is called internal direct product. So let us start. Internal direct product. Let G be a group and let H1, H2, Hn be normal subgroups of G. Okay. Then G is said to be an internal direct product of H1, H2 dot dot Hn if G equal to H1, H2 dot dot Hn and if every element G belongs to G can be uniquely expressed as G equal to H1, H2, Hn, where Hi belongs to capital Hi for all I goes from 1 to n. Okay, so this is the definition of internal direct product. Fine. The internal direct product can equivalently be presented in the following way. So let me write it as a result. Let G be a group and let H1, H2 dot dot Hn be normal subgroups of G. Okay. Then G is an internal direct product of H1, H2, Hn if and only if number 1 G equal to H1, H2 Hn, and number 2, intersection of Hi with H1 H2 Hi minus 1 Hi plus 1 Hn. This must be the trivial subgroup. Should contain only identity. Okay. So first condition remains same. Every element of G can be uniquely expressed as product of elements of HIs. This is replaced by intersection of any HI with the product of the remaining normal subgroup should contain only identity, and this should be true for all I goes from 1 to 3 dot dot n. Okay, let us prove. So first of all, let us assume that G is an internal direct product. Let G be an internal direct product of H1, H2, Hn. Okay, fine. Then by definition, G equal to H1, H2, Hn. Let G belongs to Hi intersection H1, H2, Hi minus 1, Hi plus 1, Hn. This implies G belongs to Hi and G belongs to this H1, H2, Hi minus 1, Hi plus 1 dot dot Hn. This will imply G can be expressed as G equal to, see, G is an element of Hi, so I can write G equal to E1, E2 dot dot E I minus 1, then G E I plus 1 dot dot, the last one is En, where Ej's are identity element in Hj, and I can also express G is equal to H1, H2, Hi minus 1, then Ei, Hi plus 1 dot dot up to Hn, where Ei belong to Hi is the identity element in fact, I need not write all this because these are normal subgroups of G. So actually they are identity only. So I should not write E1, E2, E3 like this. They are same. So this is E dot E dot 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 E and then E dot 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 E n times. And similarly this will be simply identity. So I can say that hi or Hj belong to capital Hj for all j belongs to the set 1, 2, 3 dot dot I minus 1, I plus 1 dot dot n to this, and E is the identity element of G, right? But G is unique since the expression for G is unique. Therefore, the nth place should be the same. So G is equal to E, and therefore Hi intersection H1, H2, Hi minus 1, Hi plus 1 dot dot Hn, this is equal to I. Okay. So one part is over. Let us prove the converse. Conversely, let H1, H2 dot dot Hn normal subgroups of G satisfying the given conditions. Okay, given conditions. What are the given conditions? Given conditions are that G is equal to H1, H2, Hn, and the expression of every element of G in terms of product of elements of Hi must be unique. Okay. Therefore, what we know, G is equal to H1, H2, Hn. That is fine. Now we'll show that every element is expressed as a product of this. Suppose we have two different expressions. Let G belong to G can be expressed as G equal to H1, H2, Hn equal to H1 prime, H2 prime, Hn prime, where Hi, comma, Hi prime, prime, Hi prime belong to capital Hi for every I goes from 1 to 3 up to n. What is our claim? We claim that Hi equal to Hi prime for all I goes from 1 to n. Okay, fine. How to do that? For that, What is HI? See, your G is equal to H1, H2, Hi dot dot up to Hn. So if I want to get Hi freely and I don't want anything else, then what to do? I have to express Hi as an element of H1, H2, Hi minus 1, Hi plus 1, etc. So let us see what actually I want. So we know that we have H1, H2, Hi, Hn. This is equal to H1 prime, Hi prime, Hn prime. Okay, fine. What to do? How to express Hi as a product of others? How to do that? Let us multiply by Hn, say Hn inverse. This will imply H1, H2, Hi dot dot Hn minus 1. If I multiply on the right side by Hn inverse, I'll get this is equal to H1 prime dot dot Hi inverse dot dot Hn prime Hn inverse. Right? We'll get that. Okay, fine. What else? This another thing. This will imply now I will multiply on the right side by Hn minus 1 inverse. Similarly, I will do the similar computation on the right side. So what I will get ultimately? I will get Hi is equal to, you will get from the left side Hi minus 1 inverse dot 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 H1 inverse Hi prime not Hi prime, will get H1, H2, H1 prime, Hi prime, Hn prime. This you will get, and on the right side you will get Hn inverse dot dot ultimately Hi plus 1 inverse. This thing you will get. Okay. This is equal to, your Hi is equal to, what is this? By reversal law, this is nothing but H1, H2, Hi minus 1 whole inverse. Then you will get H1 inverse, H2 inverse, Hi inverse dot dot Hn inverse, and then this will be hi plus 1 dot dot hn whole inverse, right? Okay, this thing. Yeah. Now what to do? Somehow we have to get rid of hi prime on this side. How to do that? I think I have to modify some steps. Let us not do this. Okay, let me erase this line. It can be simplified. So what should I do? Yeah, let us use one result. If you recall, this is not a part, but if you recall, we proved something that if H1 and H2 are normal subgroups of a group G, and if H1 intersection H2 is the trivial subgroup containing identity element, then elements of H1 and H2 commutes. That means H1 H2 is same as H2 H1 for every H1 belongs to capital H1 and for every H2 belongs to capital H2. Okay, fine. So if I use this, then see this line also not required. From this we can do. Yeah. So this implies you fix your I and then you see, let us multiply both sides either from the left or right by h I prime inverse, say on the right, h1 h2 hi dot dot hn, and this is equal to hi prime inverse into, give bracket, h1 prime dot dot hi prime dot dot hn prime. Okay, but see, hi and h1, they are mutually disjoint, their intersection is identity from this condition. From the second condition, any two h you take, h1 h2 h2 h3, their intersection must be trivial, because if you take hi and hj is a subset of this product. So if the product with hi contains only identity, then hi intersection hj will contain only identity. So here this hi inverse, this will commute with every element. So ultimately you can go up to hi prime, and in this side also similar thing happen. So here you will get h1 h2, and then you will find hi hi prime inverse and then dot dot hn, and here this will vanish. You will have simply h1 prime h2 prime hi minus 1 prime hi plus 1 prime dot dot hn prime. correct? You will get this. Okay. Now let us do the same thing. If I, this is not required. If I apply this process with every element H1, H2, H3, whatever, then what will happen? Let us go on multiplying and let us do like this. You will get ultimately you will get that your hi prime inverse, this will be equal to, now I will multiply by this inverse and so on. I will get ultimately h1 inverse h1 prime into h2 inverse h2 prime, and this may be h1 prime hi. Yeah. Okay. This is actually prime inverse this, and so on. Hi minus 1 inverse hi minus 1 dot dot, you will get hn inverse hn prime, right? This is an element of hi, this is an element of the product. By condition 2, definitely the intersection contains identity, so hi, this will be this, okay, hi prime inverse hi, this is identity, and this will imply hi equal to hi prime. So this is true for every I, hence G equal to h1, h2, hn is the unique expression, for G, expression for G. Hence G is the IDP. Let us not write short form, the internal direct product of h1, h2, h. This proves the result. Okay, fine. Next, let us see the relationship between internal direct product and external direct product. So, result, let G be a group and suppose G is an internal direct product of H1, H2, Hn. Now H1, H2, Hn are also groups. If capital H is the external direct product, is the external direct product of H1, H2, Hn, then G and H are isomorphic. Then G is isomorphic to H. So that means basically there is no difference between internal direct product and external direct product. You have a group, you know that this group is internal direct product of n number of normal subgroups. But normal subgroups are also groups. So you can consider external direct product of the normal subgroups. The resulting group, whether it is the same as G, the answer is yes, they are isomorphic. So algebraically same. We have to prove it. Okay, it is proved. Proof. We define function f from H to G by f of any element of H. H is external direct product of H1, H2, Hn. So any element of capital H will be of the form n-tuple H1, H2, Hn. And this is equal to every element of G is unique product of H1, H2, Hn. So we define it as H1, H2, Hn. For every small hi belongs to capital Hi, and I goes from 1 to 3 up to n. This is how it is defined. Now, at the beginning, we have to prove that the function is well defined. So let h1, h2, hn, comma, h1, h2, h1 prime, h2 prime, hn prime belong to H be such that they are same. H1, H2, Hn, they are same, equal to H1 prime, H2 prime, Hn prime. If they are same, then component wise also they are same. So Hi must be equal to Hi prime for every I goes from 1 to n. Okay. If this is true, then definitely H1, H2, Hn is equal to H1 prime, H2 prime, Hn prime. But what is H1, H2, Hn? This is nothing but f of H1, H2, Hn. And what is H1 prime, H2 prime, Hn prime? This is f of H1 prime, H2 prime, Hn prime. So therefore, f is well defined. F is well defined. Let us prove that f is a homomorphism. We have for all H1, H2, Hn, comma, H1 prime, H2 prime, Hn prime belong to H. F of H1, H2, Hn into H1 prime, H2 prime, Hn prime. This is equal to F of H1 prime dot Hn prime. By definition, this is equal to H1 prime dot Hn prime, right? Okay, but here is the catch. Since Hj is same as Hi, so this is same as H1 H2 Hn into H1 prime dot this is product Hn prime. Why? As Hi Hj is equal to Hj Hi, and similarly Hi prime Hj prime is equal to Hj prime Hi prime for all Ij belong to the set 1, 2, 3 up to n, I not equal to j. Okay, right? Because this H1 prime, this will commute, the next one is H2, and this will also commute with that, right? Okay, so ultimately you can shift all HIs from this to that, and this is also true that HI Hj prime is same as Hj prime Hj. This is also true. So this is equal to f of the n-tuple H1 H2 Hn into f of H1 prime H2 prime Hn prime. Therefore, f is a homomorphism. Okay. Let us prove that this function is 1, 1. Let H1 H2 Hn, comma H1 prime H2 prime Hn prime belong to H, then if f of H1 H2 Hn is same as f of H1 prime H2 prime Hn prime, then this will imply H1 H2 Hn, this is same as H1 prime H2 prime Hn prime. But this product, this is H1, this product is an element of G, and every element of G is uniquely expressed as element H1, H2, H3 and so on. So this will imply Hi equal to Hi prime for every I goes from 1 to 3 dot n. Why? By definition, of IDP. Sorry, my bad habit of writing short form. This is not a standard way of writing. Internal direct product. Okay. Okay. Let us prove that. Therefore, it actually proves. This implies H1 H2 Hn is equal to H1 prime H2 prime Hn prime. Therefore, F is 1 1. We have to prove that F is onto. So let G belong to capital G. This implies there exists unique Hi in capital Hi such that G equal to H1 H2 Hn, but H equal to H1 H2 Hn. This must belong to H, because capital H is the external direct product of H1 H2 H3 Hn, and f of H will be equal to H1 H2 product Hn, that is equal to G. Therefore, f is onto. So my function f is homomorphism 1 1 and onto. Hence, f is an isomorphism and so G is isomorphic to H. Okay. Okay. Let us see more results regarding this. Next result. Let H and K be normal subgroups of a group G such that G is an internal direct product of H and K. Okay. Then G modulo H is isomorphic to K and G modulo K is isomorphic to H. So it is enough to prove only one of these two. The other will automatically follow the previous one. So let us prove the first one, that G modulo H is isomorphic to K. Proof. So Now you are a little experienced of handling this type of situation. Whenever you are given to show that a quotient group is isomorphic to a group, then you need to apply fundamental theorem on group homomorphism. So you define a homomorphism from G to K, show that it is onto, and then prove that the kernel of the homomorphism is H. That's all. So since G is an internal direct product of H and K, therefore for every G belong to G, there exists unique H belong to H and K belong to K, such that G equal to HK, right? We define a function f from G to K by f of G is equal to K for every G equal to HK belongs to G. Okay? Okay. Prove that, first of all, this is well defined. Why? Because if G equal to HK, comma, G prime equal to H prime, K prime belong to G, such that G equal to G prime, then by the definition of internal direct product, we must have K equal to K prime. In fact, H equal to H prime, but that I don't require. So this will imply f of G is equal to f of G prime. This is because of, by definition of internal direct product. Okay. Okay. So therefore f is well defined. Therefore f is well defined. One. Now let us prove homomorphism first. So let G equal to HK, G prime equal to H prime, K prime belong to G. Then f of G prime, this is equal to HK, H prime, K prime, f of, this is equal to f of, now they will commute, K will commute with H prime, so it will be H prime, K prime. Why? The reason is, since H, K are normal subgroups of G, and H intersection K is uh, the trivial subgroup because G is internal direct product of H and K. This is equal to, by definition, this is simply K prime. Okay. What is K? K is f of G and K prime is f of G prime. Okay. Therefore, your f, therefore, f is a homomorphism, right? Let us prove that f is 1, 1. We have for G equal to HK, comma G prime equal to H prime K prime belong to G, f of G is equal to f of G prime implies K equal to K prime. If K equal to K prime, this actually forces H equal to H prime, and this will imply G is equal to G prime. Therefore, F is 1, 1. Right? On to choose any element from K. Let K belong to K. This will imply I must have an element in G. K is contained in G. So this K is automatically in G. And what is f of K? Your f of K is actually f of Ek. That is nothing but K. Therefore, f is onto. So f is a homomorphism. It is 1. It is onto. Hence, sorry. I missed something. Yeah, this is the case. You see, f of G is equal to f of G prime. So you are getting that K equal to K prime. It does not mean that H equal to H prime because you do not have any information regarding G and G prime. Indeed, I don't require it to be 1, 1. I require it is onto also. So sorry. This is a mistake. It should not be 1, 1. So this is not there. Okay. So hence, f from G to K is an epimorphism. Now, if I use fundamental theorem, therefore, by fundamental theorem on group homomorphism, this G by kernel F is isomorphic to K. Now only you have to identify kernel F. We have G belongs to kernel F implies and implied by G is uh, f of G is equal to E, the identity in K, implies and implied by f of G is what? K. K is identity. G equal to HK. And this will imply your H is equal to G belong to H. Okay? And therefore, kernel F is equal to H. So you can assume let G equal to HK belong to G. Then if G belongs to kernel F, then this thing will happen. Hence, G by H is isomorphic to K. So this is the proof. You can mimic the second one, just replace interchange the roles of H and K, you will get the result. Okay. So let me stop.